Maybe get a little more of that side. So, yeah, so that should be most of it.
Cool. Could you get someone to see if they can, or like could Sarah take someone to see if they can hear?
Oh, yeah.
Just to make sure.
I don't know if we actually know.
There's a dog in that. Like, don't jinx it.
Sorry about that.
Oh, probably.
Right next to you guys. I'll go off that like super
So the video is just like
Huh?
I can see myself.
Okay. Yeah. You can see yourself. I'm talking about can you hear yourself? Like I should be able to, but
Yeah. I hope so.
think so.
God, that way you get tons on, right? So you take you too long, I gotta be hopping. I'm not super worried.
It's not good. I read a lot.
Yeah, like
Oh wow.
you're broken. They don't.
What are you up to?
Not at all. They have to give a presentation to like project community, but now the defense time.
Oh. That's the
Right.
chemistry.
Not university. I think the entire project chemistry they don't do. So their oral is very hard.
Yeah.
But once they pass that,
In some ways that makes sense because it's like if you've gotten here, you know. Yeah, no,
I didn't get that. It's only like 1 hour.
What?
I didn't get to someone.
This is a live stream. So like no, we'll be there for the events.
They really are.
Round two. Yeah. Hopefully it looks good around one.
Not the court.
Okay. Can you repeat this? Yeah.
We know he talks fast, but still he might have too much. It's my pleasure to introduce Alex Frie for his thesis defense. Alex got his bachelor's in chemistry in 2015 from St. John's University in Minnesota. And he came to UCR in the summer of 2015. Actually, when he was visiting campus, he had told me and Sam that he's interested in both atmospheric and soil science things. And for that summer, I had my first project for salt and seed planned. And we thought, great, we found the best student fitting for this topic because, as you know, air quality and salt and seed are both understanding soil and fire and then, of course, atmospheric aerosols. So he got to UCR, and soon after, he started deploying the samplers at salt and seed stations, and went with Sam and Justin actually to collect some soil and playa samples too. As with any field projects, I think field side of things always has interesting stories. And I didn't know about this story, but a few months later, they confessed that there was an accident in one of their sampling adventures. They had gone to sort of sandy part west of Salton Sea to collect samples, and they got the truck stuck. So it took a while, but I think with Alex's experience in driving snow and also having a shovel in the car for digging and collecting samples, they got the truck free, and I don't think they went back to that site. Since then, he's been very busy in the lab and has had very productive 4 years. He took the lead on all the solvency studies that I've done in the area, and also some lab work with chamber experiments and some theoretical calculations. Today, he's going to tell you some results from some of those stories. But overall, I think it's been really great pleasure to have him in the group. I've had many good, productive discussions with him on his projects and also other projects in the group and sort of future directions of these projects. We've even had many philosophical discussions about teaching and how to get students engaged. And I think also in the department, when Alex joined the group, the department was growing in terms of having more and more graduate students, and him and Claudio were on the mini GSA, and they started their initiatives to create a more friendly and I guess open environment for the grad students. And they organized some fun activities and also informational sessions for the grad students. And I think every student here has sort of benefited from that, and we're appreciative of that too. So with that, I'll just let Alex talk to you about this.
Thank you, Roya, for that very generous introduction. Today I'm going to talk to you about my dissertation work. It's kind of a long title, but I really want you to focus on the aerosol part. We'll be talking about a few different studies, look at some different aspects in aerosol research. So if you're not familiar with what an aerosol is, it's simply small particles, solid or liquid, that are suspended in the atmosphere for lengths of time. So usually they have atmospheric lifetime in the order of hours to days. to weeks, and we usually classify them in two major size classes. PM10, so these little blue spheres here, which are less than 10 microns, and PM2.5, which are less than 2.5 microns. So you can see that PM2.5 is obviously small. But in reality, these particles aren't actually blue and pink spheres in the atmosphere. They look something much more like that sand looks like, and they're much more complicated, and their characteristics depend a lot on their sources and kind of how they transport and age in the atmosphere. So what I'm going to do now is just introduce some kind of broad sources of aerosols, so we kind of have an idea of how the variability in aerosols and some of their properties. So one of the sources of aerosols that I focused on is actually mineral dust. So you can think of this as kind of flying soil. It's maybe more crystalline in nature. It looks like a soil that's now in the atmosphere. And it's one of the largest aerosol sources in the atmosphere, especially by mass. And so you can imagine there's lots of Earth's surface to be suspended by lots of wind or off a vehicle there. But you also have things that look much different. So this is the bell tower at UCR in 2016. That this is all organic aerosol. It comes from different things like traffic hydrocarbons and atmospheric chemistry. This is going to be much less crystalline, maybe more organic in nature. Lots of times we think of these as more spherical. But you can see that this is probably very different in its characteristics than maybe a mineral dust aerosol might be. But you can have other aerosols, like wildfire aerosols, that are still maybe organic carbon or carbon-based, an element of carbon-based, but they have very different properties. You can see the differences at this picture. You can see the orangeness of this aerosol. So this is acting very differently, even though it's maybe more chemically similar to smog than mineral dust. Then you also have other sources of aerosols that include bioaerosols from living things, and then like sea spray aerosol from water bodies, stuff like that. And so these aerosols all have properties. And so the property that's really on display in this photo is kind of aerosol optical properties and specifically aerosol absorption. So the reason why this photo looks orange is because there's aerosols that are filtering out those kind of blue-purple near UV wavelengths, and to our eyes it starts to look orange. And you can imagine that might have effects kind of on the atmosphere and the climate when this light's being filtered and maybe not reaching Earth's surface. Then you also have, if you put people into this equation, people are breathing this aerosol, and then they might have toxic effects. And you can think about the source of an aerosol and the composition of an aerosol might actually control its toxic effects as well. And you have other things like shape and size that are different that kind of go into all the rest of these. So the projects I'm going to talk to you about today kind of all focus on sources of aerosol something. So this first project is going to look at sources of aerosol absorption, so kind of looking at kind of what makes this look kind of orangish. And the second one's actually going to be looking at a source of uncertainty or some uncertainty in the measurements we make of aerosols. And the last one is going to be going to that solvency basin that Roy talked about and looking for the sources of dust and kind of general aerosol there. So we're going to move into this looking at heterocyclic compounds as a source of aerosol absorption for the first project. So the reason we really are concerned about aerosol optical properties in general and aerosol absorption specifically is because of climate change and the radiative forcing of the Earth. So we all kind of know why the radiative budget of the Earth is important, because we all know climate change is now becoming important. So the top of this graph this graph is showing the radiative forcing, so how much different components affect the Earth's radiation budget. On the top, you have greenhouse gases, so things like CO2, which you've heard of, like methane that you've heard of, but in the bottom box here, we have aerosols. And so one thing you might notice here is that these uncertainty bars here on the aerosols are much larger than we have for those greenhouse gases. And that's partially because they're short-lived and they emit a little bit more randomly, but also because we have a lot of uncertainty in what they actually do and the properties of these aerosols in the atmosphere. So one thing we're doing for this project is trying to reduce those uncertainty bars a little bit. So we're specifically going to zoom in on this organic carbon portion of this graph, specifically look at secondary organic aerosol. So secondary organic aerosol is aerosol that doesn't actually start as an aerosol. It starts as a gas or volatile organic compound that can then either react with an atmospheric oxidant or even cool down and eventually form particles. And so these particles are aerosol particles. And so we're asking, okay, when we have these secondary organic aerosols here, or SOA, I might say SOA a lot, I mean secondary organic aerosol. What happens to these when they interact with light, when that sunlight comes through, what's happening there? And so we measure those, and we talk about these as aerosol optical properties. So you can think of light optical and aerosol optical properties, how aerosols interact with light. And there's really a few distinct processes that can happen. The first one is a transmission. So you can have light that just goes straight through. You can imagine that if you've ever shined a flashlight through a cloud of smoke, and you see light on the other side, that's light that's been transmitted, but all that other light that doesn't go through is being undergoing extinction processes that are known as aerosol scattering or aerosol absorption. So aerosol scattering is simply the idea that light can maybe doesn't go straight the way it came from, but it can actually be redirected when it interacts with an aerosol. So you can imagine if this is in the atmosphere and it's sunlight and that light is redirected, it might be redirected away from the Earth. And so we generally think of these scattering processes as cooling in the atmosphere. Versus we also have the second extinction process here, which is aerosol absorption. And so this is actually the aerosol interacts with that light. It actually turns that light into heat, and then you have actually heating in the atmosphere. So we generally think of absorption as things that might maybe further aggravate things like greenhouse gas-driven climate change. So we measure these in aerosol populations a few different ways. So one method we use is we look at the aerosol refractive index. So the refractive index is a property that every material has, and it just describes how it interacts with light. So it has two components. It has this K component here, which is that absorption component. It's describing this kind of red process here. And then it has an N component, which describes the scattering. And so that's really kind of what we need to know about the refractive index there. It has two components, absorbing and scattering. Where we're really going to focus today on looking at the absorption component, because we're going to look for sources of aerosol absorption specifically. And the second measure that I'm going to use today to look at aerosol absorption is actually the mass absorption coefficient. So this takes, if I measure absorption for an aerosol cloud of some sort that goes to my instrument, I can divide the amount of absorption that I see by the amount of aerosol that is in the concentration of that aerosol, and I can have a mass normalized concentration of absorption, or mass normalized absorption measure. So this is very useful because it is a little bit easier to measure than the refractive index itself, but it doesn't account for things like shape effects or size effects that might occur when the particles are actually in the atmosphere. So we know a few things about what makes aerosols absorbing in the atmosphere, and so we're going to use these to kind of look for compounds that add to absorption. We know they tend to be aromatic, conjugated, highly functionalized, and generally it's easy to move electrons between orbitals, kind of tangent-dividing orbitals, so there's any chemist in there. And they generally contain nitrogen-containing species, and so that's something that's been kind of empirically observed in the atmosphere, is that aerosols with lots of nitrogen, generally organic aerosols, generally seem to be more absorbing. So we're going to use this knowledge to kind of select a few compounds that kind of fit this bill. The compounds that we chose to look at are heterocyclic compounds. So all heterocyclic means is that we have one element or one atom here that's a different element. So you can see the sulfur and thiophene, the oxygen and furan, or the nitrogen and pyrrole. So, and then we know the nitrogen is important, so we're reacting them with nitrate, which is a nitrogen compound. But we're not just pulling these out of nowhere, being like, oh, these are compounds that we want to, they seem like they should do what we want them to do. We know these compounds are actually found in the atmosphere. There's measurements of their emissions from burning of different fuels. So when you burn a fuel, you can actually measure these coming off. So these are actually atmospherically relevant compounds. And we know that nitrate is a dominant nighttime oxidant, so or can be the dominant nighttime oxidant. And so this means we have a combination of things that should happen anytime. There's wildfires that happen at night. There's these plumes travel at night, so they're probably going to be exposed to this nighttime oxidant. Then we're asking ourselves, kind of what kind of aerosol is forming? Is this kind of light absorbing aerosol, or what we also call brown carbon? So I don't think I've explained that, but I might say that a lot. Brown carbon is simply organic aerosol that's absorbing, or maybe it's going to form aerosol, but maybe that aerosol is not absorbing, or maybe it doesn't form aerosol at all. And so we're kind of asking these questions. And how we do that is we actually have a reaction chamber in our lab where we can actually form nitrate here by adding ozone and nitric oxide, and then we can add one of our heterocyclics and monitor these as they form aerosol, and look at these aerosol properties as they form. So while these are forming, we monitor them through a few different instruments. So we look at kind of the absorption and scattering that's occurring throughout the experiment with this photoacoustic extinctometer. It's a mouthful. But we also monitor online gas phase chemical properties with a chemical ionization mass spectrometer. So that looks at what compounds are forming in the gas phase that maybe can help us explain what's happening in the particle phase. So maybe we see something that might condense in the particle phase and explain some of this absorption. Then we also measure the size distribution. So how big are these particles that we're forming? How many of them are there, essentially? And then we also, at the end of an experiment, we'll take a filter, we'll put a bunch of these particles on a filter, and we'll take it to lab. So this was with the help of Dr. Lin's lab, and Juan is sitting over there, who collaborated with us in this project. Where we actually take these and you do a UV vis measurement. So you actually, as opposed to having absorption measurement at one wavelength, that's going to be in solution at a lot of wavelengths. So we can do it from like 300 to 800, I think. And we can also take that and do offline mass spectroscopy, where we can actually look at what are those compounds that are actually in the particles for their absorption. And so now I'm going to move into the results of these, if it goes. Okay. So this is the online optical results, specifically looking at that refractive index values. Remember, K is absorbing and is scattering. We're going to look at K. So the first thing you notice here is that we only have 2 compounds, and we did 3 compounds experiments. So that's because that furan compound, that oxygen-containing compound, had a really low aerosol yield, so there weren't very many particles that formed. And particles that did form didn't have enough absorption to really get significantly above our detection limit in our instrument. So we said, okay, we're not going to try to calculate these refractive index values here because we can't confidently calculate them, and it seems to be pretty non-absorbing. The other thing you can get from this plot is as our experiment goes on, it's pretty clear that this pyrrole SOA, secondary organic aerosol, has a higher K value, so it's more absorbing than this thiophene SOA. So this kind of makes sense if you remember those things I said that absorbing aerosols have. The pyrrole has more nitrogen, and nitrogen we seem to think is related to absorbing aerosols. But both of these make absorbing aerosol in this measure. And we can look at how this K value compares with some other secondary organic aerosol experiments. These other ones, so these 2 here are our experiments that I'm talking about right now. All the ones to the left are experiments that have been done with OH as an oxidant, so that represents more daytime chemistry as opposed to nighttime chemistry. And we can see our 2 compounds here in green, and you can see pyrrole here seems to be among the most absorbing that I have here, similar to this other compound, 1-methanaphthalene, that our lab has identified as a potential source of absorbing SOA as well. And then thiophene seems to be slightly absorbing, and kind of on the level of some of these other aromatic compounds. As opposed to these 2 that seem almost non-absorbing, those are kind of basic biogenic, they're things you might expect to come from plants. They seem to not be absorbing on their own. Then we can move to these offline optical results. So we took filters, we took them and extracted them with methanol, and then looked at them on the UV-Vis. And so we see pretty much the same thing. So we were able to get enough furan on the filter to look at absorption here, even though we weren't on the online instruments. We see that pyrrole seems to have the most absorption, kind of at a broad spectrum of wavelengths, although thiophene seems to be more comparable in the extract. So that could be due to things like chemistry that might occur during the extraction, or maybe even solvent effects that make this, because it's not online, there might be some different changes that occur in the aerosol. But then again, furan seems to be the lowest, although it does seem to have some absorption at low wavelengths. And then we also, again, had those online chemical observations. So we had that online mass spectrometer, which monitors different species in the gas phase. So we're able to look specifically for the molecular formulas of compounds we think should form in this experiment. And then we can say, okay, how do these change over the course of the experiment? So what I have here are just kind of those base compounds with the addition of a nitrate species here. And then we see that these signals tend to increase over the course of the experiments. And then I have another product here, which is a nitro group that seems to also increase over the course of the experiments. So this says, okay, it seems like we have some reactions that are actually occurring with the nitrate in our hydroxylic compounds. One thing I do want to point out is these are not necessarily the exact molecular formulas, or not the exact structures, because from these mass spec we get a signal at a certain mass that we then correlate to a molecular formula, and then we predict maybe what the structure may be. So these nitrate groups may be somewhere else, or they could have a different isomer. But then we also want to look, can we see these in the particle phase on that LCMS, so on that offline aspect. So if you're not familiar with chromatograms, on the bottom we have retention time, on the left axis we have signal. And then for these ones, we've extracted one ion. So we're looking specifically for nitropyrrole, which we saw in the gas phase, the nitrothiophene, which we didn't see in the gas phase, but we think might be a potential product in the particle. We're not looking at those nitrate groups here because we weren't able to see them on LCMS, so we didn't have a signal on the particle themselves. And then, so the peaks there are when these compounds are coming out of the chromatograph here, and then we're seeing them in the mass spec. Because what we can do is we can actually look and see what does that optical spectrum look like during these times when our potential chromophores are actually coming out here. So we take those times and we can kind of look at an optical spectrum that's being measured. So this is similar to that max spectra that we had before. And we can see that this is what this looks like kind of at this time. And then if we take these 2 times here, we can look at this optical spectrum here. And we can select what we think the peak wavelength for these compounds would be based on what we're seeing here. then look at that chromatograph, kind of the absorption chromatograph for 340, which is this peak here, and then for 310, which is this peak here. And so what that shows us is we do have peaks in absorption that kind of align with when these species are eluting out of the chromatograph, which tells us that we do have, these compounds are having some absorption. But you can also see there's lots of things here and here that seem to be not explained by these two peaks. And so what that tells us is we have unidentified chromophores. So I don't know if I explained chromophore, I use it a lot. It just means light absorbing compound there. We have unidentified chromophores. And so that's okay. It leaves some more questions to pursue in the future to kind of see if we want to identify more chromophores here. But I'm also interested in the potential impact, right? So we really want to know, why does this matter? How important are these relative to maybe some other compounds? And so we can do this because I said earlier that we have actually measurements of how much of these compounds come out of different fields. So somebody's went and they burned fields and they looked at, okay, how many grams of furan, how many grams of thiophene, how many grams of pyrrole are coming out. And we also know kind of the mass of particles that form from the reactions that we did in the chambers from a dip starting concentration. So we can kind of take these, put them together, and then estimate the potential secondary organic aerosol through this process. So kind of a potential, if you burned this, it all went through here, this is how much aerosol you can get. And we can also use, there's potential SOA estimates from Hatch et al. Here that actually estimate the total amount of secondary organic aerosol you get from the daytime oxidation processes. So we can compare what we expect from this process for these specific compounds relative to all compounds for the daytime process. And so that's what this next graph's going to be. And so on the bottom axis here, I have the different compounds that we did. And then one kind of test compound. So toluene is kind of it's a pretty common compound in the atmosphere, or admittedly compound. And so we did the same calculations with it. On the left axis is the relative amount we expect through if all of the pyrrole went through this process compared to all of the daytime process. And so what you see here is that for fuel, and then so the colors represent different fuels that you burned. So we have different fuels, different compounds, and then compared to the relative amount of OH. So we see here, especially for pyrrole, it seems like these are pretty significant relative to the OH pathway. That you have things that for fuels like rice straw, that maybe something like 20% or SOA mass could have been coming from pyrrole. So these seem to be potentially important processes. And what this really tells us that if we want to go see if this is actually a pathway in the atmosphere, we should maybe go look to see where rice straw and wiregrass burning is occurring and look at now the smoke results. Because if we don't see it there as a large portion of SOA mass, it's maybe not important at all. But we also want to look at kind of how, which one of these compounds is actually the most absorbing or will maybe lead to the most absorption in the atmosphere. So we can do the same calculation, but we get rid of that relative point because there's no relative absorption for the total smoke cloud from these ones. But we can look at the absolute absorption and multiply it kind of by that map value that we have. And then we get what we call the potential absorption cross-section for different fuels. This looks different than that other graph because we're not normalizing to that OH, the OH mass. But we still see that pyrrole is going to be very important, and that for fuels like ponderosa pine, pyrrole pathway might be really important for absorption. We might have quite a bit of absorption coming from fuels like that. So it seems like these are important precursors to aerosol absorption and maybe even aerosol mass. So in conclusions for this part, seems like these heterocyclic compounds are important. So when I say BRC, I mean brown carbon. Sorry for not introducing that. Nitrate and nitrous species seem to be present in these reaction systems. They seem to possibly be explaining some of the absorption that we're seeing. And then if we're looking for further evidence of pyrrole source chromophores, maybe we should look in straw and rice grass-based emissions based on kind of their overall portion of the SOA mass we predict might occur. And then the other thing we can kind of take away from this is furan is kind of a large, it's a large product from burning processes. There's usually quite a bit of it. We see lots of it, but it seems like it has a pretty low SOA yield, which isn't, we're not the only ones to see that. And the absorption seems to be relatively low as well. So maybe this compound, even though there's lots of it, is less important on the secondary organic aerosols. Okay, and so now I'm going to move to the second project, and I'm going to briefly overview this project, just for the sake of time. This is something that's kind of come out of doing the refractive index calculations, as I really wanted to better constrain the uncertainty of these. So this one is going to be a very quick overview of looking at the uncertainty of aerosol refractive index calculations. So again, aerosol refractive index has two components that describe how that material interacts with light. how we actually measure this is we observe these optical properties using that online instrument for a given aerosol observed size distribution. Okay, so we know how many aerosols are there, or particles are there. We know what size they are, and we know what we're seeing for absorption and scattering. And then what we do is we choose a bunch of possible refractive index values. We actually use what's called mean theory to predict what we think would happen if these were the true N and K values, what the observed scattering in absorption would be. So we have predicted optical properties and we have observed optical properties. And so then you just say, okay, which of the predicted optical properties are the most similar to what we observe? So pretty straightforward on that point. And so then we just take as the true N and the true K as the most similar values to the ones we observe, or as the most similar absorption in scattering. The issue with this is that the sensitivity to uncertainties in diameter, in absorption, and scattering, and particle size changes based on your particle diameter and changes based on your actual refractive index. So it's really hard to actually constrain the uncertainty from just doing one uncertainty test because your uncertainty will change based on your conditions of your aerosol population. So we did kind of what can be thought of as a bootstrap, where we take close values and see if we can get them to give the value that we got. So if we look at refractive index that are near, we perturb the inputs with uncertainty and we run the calculation lots of times and eventually get something that's kind of a probability distribution here. So each one of these red dots is a value that we tested to see if we could get on this, in this case, the kind of one we were testing for was 1.2. And then it's all normalized by the kind of normalized the total ones that were able to give us it. And we fit this with the sigmoid. And with this, we're actually able to calculate a confidence interval here and say, okay, we calculated 1.2, but we really think it's somewhere between 1.18 and 1.212 or something like that. So from this, we can start to account for differences in the uncertainty that are caused by things like the size distribution in the specific NK value. And so, like I said, I'm not going to go too much more into that right now, but just looking at uncertainty in this calculation, that is very important when we do things like upcalculate the radiative forcing of aerosols in the atmosphere. So if you want to put this in the model, it's really important to understand your uncertainty in your practical indexes. And lastly, I'm going to move to that third project, so looking at the Salton Sea Basin, which I think is what I talked about and what I'm perhaps most known for working on. It's what I presented for the last 3 or 4 years. So we're going to move back to Southern California, out of the lab, and go to the Salton Sea, which is the second largest lake west of Mississippi in the U.S. It's the largest lake in California, and it's about 2 hours southeast of here. So it's pretty large and close. The reason we're going there originally is because this has poor air quality already. So essentially, since PM10 standards are created, we've known this area has poor air quality. And we also know that this area has very high childhood asthma rates, as well as a large income disparity. So it has a large kind of environmental justice question. And so this is just kind of the general rate of Imperial County, which is kind of where the Salton Sea is compared to California, which isn't known for good air quality, for childhood asthma hospitalizations in, I think, 2017, I believe. So the area has poor air quality. In addition to this, we have this large lake that's shrinking. And so this is related to air quality because as this lake shrinks, it reveals what's submerged lake bed, and now is dry lake bed, which is known as playa, which we know in other cases, in other examples in the world, can be a large and significant dust source. Sorry, I'm stumbling a little bit. And so the predicted exposure of dry lake bed or playa is expected to be about 400 square kilometers when this lake restabilizes after all the water kind of management conservation changes go. And so this graph shows the area of the Salton Sea, and the red shows the predicted area once it's gone. So you can see, or once it's stabilized. So you can see all of this will be exposed. And the reason we really worry about this is this. So this is me just touching that playa surface. It's not always like this, but it's like this sometimes. And then it just falls apart like a flower. And so you can imagine if wind comes over this, it's maybe much more emissive than a typical desert surface. So that's why we worry about this type of surface more than maybe you might worry about a typical desert. And other reasons we might want to worry about this is because we know, in mineral dust specifically, this type of aerosol, is because we know that these are important for transporting nutrients and contaminants to soil, specifically in remote environments. So you can think of places like Hawaii are almost completely dependent on dust deposition for things like phosphorus. We know that emissions have been increased in the American Southwest by some estimates up to 4% a year. So if that's your return on a stock, that's great. If that's your return on your dust emission, not so much. But it also can affect things like snow albedo. So if you have higher dust emissions, you can have quicker melting of snow in mountains, which means you have maybe less water security in those areas. And then I want to take a moment and talk about this image here. So this is Owen's Dry Lake, which is kind of the worst case scenario for the Salton Sea. In the late 1900s, it was the largest PM10 source point source in the US. And since then, the city of LA has spent over $1 billion mitigating dust emissions. Because it had such amazing effects and horrible effects on air quality. Maybe astounding and horrible. So this is kind of what we're worried about happening with the Salton Sea. It serves as kind of an analogous system we can actually compare our data to. So the first thing that we did is when I first got here, did that very first project, we did a two-time sampling campaign. We went out in the summer of 2015. That's when we got stuck in the desert, 110-degree weather, in the winter of 2016. And so we actually took soil measurements to kind of look at what the source composition looks like in kind of the local soils as well as on these playa surfaces. And then we also actively sampled aerosols for about 2 weeks in the summer, 2 weeks in the winter. And then looked at their composition, looked at ICMS and metal composition, and tried to predict how much of these particles were coming from maybe this typical desert surface versus these dry lake bed surfaces. And so this schematic is kind of a summary of what we found in that initial work. We found that a large, probably the lion's quantity of PM10s can be coming from this desert dust. We seem to say that on any given day, probably about 10% of PM10 is coming from the playa, but it's changing the composition of the playa by adding things like soap. It seems to be simply more salty. Then we also saw an interesting thing. So selenium is an element of interest at the Salton Sea, simply because it's in high concentrations in the water, it's in high concentrations in the soil. It has potential bird and fish toxicity. I think bird toxicity really implications. So and we saw interesting things for selenium where we thought maybe we see some seasonal variations that suggest selenium is actually being degassed into the atmosphere in certain seasons. Potentially, people who work with selenium are interested in that. But we really decided we want to go out there for more than just 2 short sampling campaigns. We want to get longer term data, see if we can think about the seasonal variation and the spatial variation. So this is, we deployed at 5 different sampling sites in the Salton Sea Basin. Kind of moving down, we have Palm Desert, which is the most urban site, Boyd Deep, which is close to kind of the urban area, but its own kind of mountain canyon. We have Dos Palmas here, which is close to the Salton Sea, but off into the desert a little more. And Worcester, which is got a little bird, because it's a bird refuge and has lots of marshes. And so it's a little, so that's kind of remind you of that. And then Sunny Bono site, where this blue and the gray is supposed to kind of show this is playa. This is that dry lake bed surface. This is actually on the playa bed. And we actually deployed long-term, semi-long-term passive samplers here. And so these are very simple in nature. So they're literally just an angel food cake pan with a Kevlar mesh and set in there. The marbles put on top. We put it on this post and we leave it there for a month. And we come back and take it down. So the idea here is that if air mass with dust in it comes and interacts with our sampler, some of that dust will get entrained in our sampler and then maybe caught below these marbles. And then won't be able to get resuspended. So we're kind of passively collecting dust here. And so if we were doing this and the first people to do this, you might be like, why would you ever do that? But we also have a long history, probably 20 years of data we can pull from in the American Southwest. So we're not the only ones that are using these simple samples. It also allows us to do things like not need electricity or some of the logistical challenges that you have when you're going to a place that's kind of remote and very hot. So we put these out for a month at a time between May 2017 and May 2018. And then we brought them back to lab and we looked at how much mass is in them, so the mass flux. And we looked at the total elemental composition of each one of these samples. So we looked at all these elements. We looked at soluble anions in these, and then we used a software called positive matrix factorization to kind of tease out what sources were important, when, and where. And so, and I'll explain that a little bit more when I get to that part of the data. But first, I want to talk about the mass flux and some of the historic data. So this is a map of sites where these samplers have been deployed kind of since 1984. So these black ones are our samplers. These purple ones are kind of what we classified as general California, Nevada. And then these two other areas are kind of high dust basins. So Owens Lake Basin, where that large lake where we saw that testimony pictures happening, and then Soda Basin, which is known to be like the sand corridors. And then we can compare our results to their results. And so what we see is that relative to kind of the background in normal desert levels, most of our sites are higher here than the average and median. And you might say that they're more similar to what we're seeing at Soda Basin or Owens Lake Basin. So it seems like this is a high dust environment. So we know it has poor air quality. It makes sense that it's a high dust environment. The other thing you can pull from this is that if you look at this on playa site at San Ipono, it has double the mass flux of all the other sites we look at. So it seems like that site seems to have a very high mass flux. And the other useful thing to do is zoom in a little bit more on these on playa sites and look at the site that was deployed on the playa at that Owens Lake relative to the site that we have on the playa at Salton Sea. And so this site was deployed for 11 years, between 91 and 02. And they're kind of, sorry, there's no units on here. Fix that. That's grams per meter squared per year. And so what you can see is that the dust flux at Owens Lake Playa was much higher than what we see at Salton Sea Playa. But we still see a very high dust flux at Salton Sea Playa. But you can also kind of look at, okay, what's the area exposed at Owens Lake Playa? You had 280 square kilometers. What's the area exposed to Salton Sea Playa? You have about 75, right? And then you can look at what we think might be exposed, kind of if the current course doesn't change. So we don't know if this will scale linear to area, but you can kind of do a little back of the envelope calculation, in that you can think about maybe the Salton Sea might become as bad or as big of a dust source as Owens Lake was, if these start to scale linearly for these dust sources. So generally, we're saying this is a very large dust source. It has potential to be on a similar scale to what we saw at Owens Lake in the late 1900s. And so now we want to look at where this dust is coming from, not just how much there is there. So we're going to use this positive matrix factorization, or PMF. So what this does is it isolates source profiles. So it says, okay, this source has lots of sodium, but not very much iron. And it does that by looking at the variation in these different compounds over the whole sample set. It also does things like weighting by error. So if we know we have no confidence in how much phosphorus or phosphate is there, it's really not going to let that determine what our source factors look like. So we can do things like if it can account for things that we're less confident in measurements in, or if we have low detection limit measurements, we can kind of account for that. And then it also doesn't contain negative values because the idea is that you can't really have a source that's contributing a negative amount to your to the kind of the dust or the what we're seeing here. So what we do is we put in the elemental mass and anion concentrations from each sample that we have, so all of those samples, and then we look at the total, and we also add the total collected mass as a super downweighted variable, so we can kind of predict how much mass is associated with each one of these sources. So, but it doesn't drive that source profile. So now I'm going to show you what this actually looks like. I'm going to walk you through a few of our sources. So we identified 7 different sources in the Salton Sea Basin that ended up in our pans. And I'm going to walk you through kind of how we're going to look at these here by looking at this first source, which we've identified as anthropogenic trace metals. So if you're not, so anthropogenic simply means human cause. So we're thinking these are trace metals that are driven by human activities. So on this left axis here, I'm going to show you the relative mass contributions, and I'm going to show it to you on bars. So this is just saying, this is the mass of barium that we think is in this source, but this is the mass of sodium. This is on a log scale. On its own, this is a little bit hard to look at. There's a lot of data there. We're going to be going, but we have other things. But we have other ways to look at this data that might help us understand this source a little better. So we actually can do, what we can do is we can say, okay, we sampled this much sulfate here. How much of the sulfate, all of the sulfate that we sampled, do we think came from this source? And so the percentage that came from this source in all the samples that we have. And that might help make this a little bit easier to look at. And we can start to see that even though these things have very different concentrations, what might be really important here is this seems to be really important for the activity source. On this axis, we're crediting this source for about 90% of the activity. So using this, we can start to think about why we label this anthropogenic trace metals. Because some of these things that we know have high percentage attributions are trace metals that are commonly associated with human activity. And then to make this a little more clear, we can weight these dots by uncertainty. So what I've done is that the bigger dots are now more confident dots. So we can now see we're pretty confident that we have antimony in this source. We're pretty confident with things like cadmium, lead, arsenic, and a little bit of sodium. And so using these, we can now understand that, okay, we have lots of trace metals that we know from from previous studies that's associated with anthropogenic sources. And so we can identify this source as anthropogenic trace metals. So hopefully now you kind of understand what's going on in this graph. I'm going to show you a few more of these. Before I do that, I'm going to explain a second complicated graph that I have. So this is the variation in space and time of this one source. So so on the left axis, you're going to have these sites that we're sampling at with their fun little symbols. And then we're going to kind of have in each different column, we're going to have each box, we're going to have the intensity of that source, and each column you're going to have a month. So for this 1 month of May, we can see that this is very dark blue here, and dark blue is the strongest. So we at Palm Desert site in the month of May, we had a very strong contribution of the anthropogenic trace metals here. Versus we had a much weaker concentration at kind of those middle ones, and maybe kind of a middling concentration at Sunny Park. Then I'm going to add one more piece of information to the bottom of this. And so this is going to be kind of a wind descriptor. So these are going to be arrows that are sized by the wind speed. So bigger means wind is faster. And then they're pointing in the predominant direction of wind during that sampling period. And then we can fill this in for a whole sampling period. And so kind of one thing before we get too into this, you can see there's a general trend in wind that it goes from west to east kind of in the summer months and then switches to north to south in the winter months. And I'm also going to point out here that you might notice there's no March here. And that's because we sampled approximately monthly, not actually monthly. And so we actually have 11 samples, and March is kind of split into this February and April. So if you have questions about that, we can talk about it. But then now we can look at this source specifically here. You can see that it has very strong contributions at Palm Desert, kind of in the summer months. So remember, this PD Palm Desert source or sampling site is in an urban area. So if this is anthropogenic, it makes sense that we're seeing it there. But then we can ask ourselves, why do we start to see it everywhere, kind of in these winter months? And so one reason that this might be is because we have this switch in kind of predominant wind direction during these winter months, which allows the source to be more distributed throughout the basin. And we start to see it more because it's now being transported kind of south into our other sites. So what you can see how through this sampling, we can now understand kind of, we have this source. It seems to be important at Palm Desert, but it's important basin-wide in the winter. So we can understand the spatial distribution as well as its seasonality and start to explain why it has a seasonality. And then now I'm going to move to the second source. So this is another anthropogenic source. You can see this one looks very different from the other one. We really only have a confident measurement or confident attribution of copper here. So copper is a common thing that's also associated with kind of human activity. It's in things like brake pads, so it can be aerosolized that way. And when we look at the kind of spatial distribution, temporal distribution, we see now real trend. We actually have about 5 very distinct kind of detects. And so what this tells us is maybe this is a more localized source, like something like maybe you have to have somebody drive by with that brake pads or something. And so I guess, when I say localized, I point at these very strong signals here, not kind of this green basin-wide. So if we look, green's actually a pretty low contribution. So it seems to be maybe basin-wide, but it seems to be very strong in a few very specific sources, samples. And so the next one I'm going to show you is biomass burning. And specifically, we think this is agricultural biomass burning here. And so we've identified this kind of by looking at this soluble phosphate here, as well as if you look, potassium is a little higher and a little more confident. And so we know potassium is a tracer of biomass burning emissions kind of in the aerosol community. We know that biomass burning is a common method of kind of phosphate redistribution in the environment. And we can validate this by looking again at our kind of spatial and temporal distribution. And we can see that we see this at these 2 sites, which are closest to these agricultural areas in the south. And so this makes sense. So if we have burning, agricultural burning specifically, of crops or kind of field waste, you will detect those at this site. And it seems to be kind of all seasons generally. So I tried to look at some data of when we should expect to have burning in the Salton Sea Basin. There's not a lot of reporting in the literature on that, but there is some indicating that it is at least happens in the winter into the summer. So it's pretty seasonally independent, should we see. And then you really don't see it much kind of at these higher ones, up here. Maybe you see some here in May at these more northern sites, and that could be because these wind directions might be more likely to move stuff up more. And then we're going to have what is commonly identified source sea spray. So you have, again, chloride, selenium, which is again common in the Salton Sea waters, and then sodium. So these are all things we kind of expect to be in the sea. And we can look at when and where do we see this? We see it. It seems to be, you see some of it kind of basin wide, but you see it most strongly at these two sites that are right next to the sea. So we think this is just from wave action on putting aerosols into the air. And then now I'm going to move into the sources that are actually those dust sources that perhaps we think of as being the most important for air quality. And so we're going to have three of those being applied. So the first thing I'm going to discuss is something we've defined as Colorado alluvium. So if you study soil science, you might know what alluvium is, but if you haven't, alluvium is simply soils that are formed through moving through water, or soils that are from movement or have been moved through water. And the Colorado part of this, in this case, they've been moved by the Colorado River. And so what I want to get from this composition graph is that we have high concentrations, high attribution of uranium, but we also have kind of high confident contributions of a lot of what we call crustal elements, things we typically associate with soils. And then I also want you to look specifically, first, the only time I want you to look at the bar graph, maybe one of the two times, is that this calcium is higher than this aluminum. And so this is going to be diagnostic, and showing this is Colorado aluminum, Colorado soils from the Colorado River, as opposed to other soils. And so you may be like, well, where's the Colorado River? So this actual basin where the Salton Sea is used to be underneath what's the ancient Lake Huia here, and that spanned most of this basin, and this is the Salton Sea, so a much larger component. Most of this land is actually now used for agriculture. The Salton Sea itself is actually from Colorado River water. It was accidentally filled in 1905, and this is a picture of what that happened when that happened. So some people, I think we had a speaker a few weeks ago that referred to this basin as the reverse Grand Canyon. There's lots of sediment from the Colorado River that's been transported here over the course of its geologic history. Then we can look at, so this is a little hard to see on the screen, but this is the concentration of calcium kind of in a bunch of different sediments and soils that was measured by the USGS. And what you see is that we have high concentrations in this area that's kind of agricultural use and kind of in this basin, and lower concentrations in the surrounding mountains. And so this allows us to say, okay, if we're pulling out calcium as high in the source, perhaps it's coming from these soils. And we also know that these are agricultural use. And when we look at this temporal distribution, we see a temporal distribution that kind of aligns as if these soils are being used for agricultural use, especially because we know that this is a winter crop area, or it's kind of, I believe there's crops in both seasons, but I think winter is the major season. So we see a large decrease in this dust source in the winter, as opposed to the summer when you see it at almost all sites in the basin. So this site, Colorado alluvium, it's soils that have been formed from the sediment that transported from the Colorado River. And then most of them seem to be developed for agriculture, and so we have seasonality that seems to be driven by the actual agricultural use. Then we can move, here's another image of this. So this is actually an image to kind of prove that I'm not making up the agricultural use. So this is satellite imagery of January 11, 2018, and you can see all the green here, that's supposed to be vegetation. And then August 19, 2017, so there still is some things that are used, but it's so hot in this basin that I believe it's difficult. It's more difficult to grow in this season. So this is the major focus. And then we have a second alluvium source. So this is local alluvium. So this is things that are washing out of the local mountains and forming soils that way. You can see again we're confident in more of these cluster elements here, but if we look at this kind of calcium and aluminum ratio, aluminum is now much higher here. And if we look at these other USGS data here, we can see that aluminum concentration is pretty low in the Salton Sea Basin. It seems to be higher in the surrounding mountains. So this, and in kind of this northern area that wasn't under Lake Huia, is also would be what we think of as this local alluvium. So this seems to say that this is more local dust source. And we see this one pretty much basin-wide. It seems to be stronger at the north end of the basin, and that's well explained. So if you've ever driven that direction and seen all those windmills, it may have been dusty. So that's the kind of whitewater alluvial fan. That's a well-known dust source and kind of an important thing for air quality considerations in the kind of the Coachella and Imperial Valley. And that explains well why we see highest concentration of this source at Palm Desert is because of that kind of large alluvial fan at the north. But we do see this basin wide, which makes sense. And then maybe a little bit stronger in the summer when we have the strongest wind speeds by the size there. And lastly, but certainly not least, we have what we've identified as the playa source. So this source we've identified by kind of evaporite mineral and salt species. So you can have things like sulfate, strontium, calcium, magnesium, potassium. Those things you might think of as being your salt shaker or your Epsom salt. But in this case, for playas, they actually form the playa surfaces because you have water that moves up through the ground. You actually deposit these salts, and they actually become a signature of playa emissions. So if you have lots of evaporite minerals, they're kind of salty composition. And so we can now look at when and where do we see this. And we can see that we don't see it very often in our samplers. We really see it, it's highly seasonal. We see it very strongly kind of between February and June. So February and April here, May and June here. We really don't see it in the summer. And so this is partially explained by wind speeds, but it also can be explained by playa dynamics. We know that playas sometimes can form hard crusts that don't emit, and then these crusts, they interact with rain in a unique way that rain can destroy hard crusts and help make more emissive crusts. So you can think not only is it more rainy between February and June, but it's also more windy. So you can have these things that become more emissive during the season. And we can potentially use this if we're interested in mitigating kind of these emissions in the playa. To potentially, we should be applying mitigation during these months. Maybe the summer is not as important. And then the last thing, we really want to look at what's the source of the mass, right? We're really interested in the kind of what's driving these PM10 concentrations here. So what I have here are these two kind of temporal distributions of the mass attributions. So, and the ones that are really important here are the blue and the playa here. And then the green is that local alluvium, the yellow is the Colorado alluvium, and this brown is the biomass. And the other thing to point out here is this April sample is 1/10 of its actual signal, because otherwise it would overcome it. And so what this shows us is that these playas are becoming very important for mass at that Sunny Bono site. This seems to be a really important mass source right now. And it's a really high magnitude. But if you were to take this away, think about maybe, we already had poor local air quality. What's causing that? It seems to be a combination of this Colorado alluvium, so there's things that are being used for agricultural use, and this kind of local alluvium, which is kind of the rest of the so kind of to summarize here, one thing, most of the dust sources we've identified are in some way influenced by engineering activity. We can think of those few ones that have anthropogenic in the name. The sea spray, the Salton Sea, is caused by we filled this up, so that's why it's there. These playas are a source of our water management. That's why they're there. They wouldn't be there if we didn't put any water into the basin, at least not in this form. That Colorado alluvium is controlled by agricultural activity, so we seem to be kind of controlling that one. And there's likely that local alluvium is also controlled by things like off-road vehicle use in construction. We also observe seasonal facts that can kind of explain when and where we see these sources. Specifically for playa sources, this might mean that we can target mitigation effects for these seasons we know playas be more emissive. And then identifying mineral dust sources can generally give us, rather than identifying them as mineral dust completely, which is not uncommon in kind of our field, the aerosol field, if we go and look at individual sources, we can start to say more about what processes are actually, what activities are important for kind of air quality, dust emissions. So just to summarize, we've done 3 projects looking at sources of aerosol absorption, sources of uncertainty and refractive index calculations, and then sources of aerosols themselves in the Salton Sea basin. And so I'd like to thank kind of our scientific collaborators here first. Gordon Bree's lab, which is our lab itself, Misha's Lynn lab we collaborated with, and Tim Lyons' lab in geology, Sam Means lab, Aaron Smith's lab, Hufford Zane's lab. I'd like to thank Alexis Garrison, who's here. She washed all those marbles and pans in order to measure those dust fluxes, so it wouldn't be possible without her. And then David Lyons, who helped with some of that IC analysis. And then thanks to our funding here. So there are a few different funding sources from UCR, but also from NSF and USDA. And then thanks to my committee. So I've been lucky that not only is my committee been my committee, but they've also been collaborators throughout my course in the PhD. So I've been able to work with my committee, not just have them give me edits. And then thanks to all the friends and family who've been there over the years for the hard parts and the good parts, and have supported our journey throughout graduate school. There's been people that have left since I've been here that will miss, and I'm sure I'll miss all of you once I leave as well. And then lastly, I'd like to thank my wife, who just got her PhD, so you can congratulate her as well. It's not just in making funny faces, but she did support me through our whole time here as well. So. And lastly, we'd like to open it up for questions from the audience, I believe. So thank you for coming.
All right. Any questions for Alex? Yes.
Great presentation, wonderful job. I was wondering, I was looking at the information sources and maybe attributing some of these variability to like your traffic, since obviously people are going to the desert more in the winter, towards the winter there, versus in the summer where it's absolutely too hot to go. Did you see any different variabilities maybe?
So I didn't look directly at that. So I did at some point try to look at traffic, but you're definitely right that especially in this area you see lots of things like I tried to look at off-road vehicle activity specifically and wasn't able to like link HPV to like an off-road vehicle use there. But potentially if this is a major traffic emission, that could also help explain that maybe it's not just wind that explains kind of that variation. But yes, that's a great question to think about traffic, especially in an area that's not very
So I'm really curious about the aluminum and calcium interactions that you had on those maps. So like there's really polar relationships in the agricultural area where you have this really low calcium, right? And then the really high aluminum, right? Is that correct?
So high calcium will.
Okay, what's happening in those agricultural areas that's causing that to be such a unique?
So I'm not actually sure why aluminum is low in these soils, but calcium enrichment specifically makes sense for kind of well irrigated soils because you think of soil salinity, calcium is a soluble cation that can potentially be increased this way. But also I think it's a function of again the sediments that are moved down to the Colorado River Basin have a different composition than those. Like they form different geologically, so they're different than maybe what's natural in the mountains here.
Do you know if they apply limestone to these agricultural fields, which would be
I don't
calcium carbonate?
Yeah, but I don't know if soil acidity is a huge problem in the Valley. But I'm sure like Dr. Wu, who's definitely left, and some of the other, maybe even Sam, might be able to type in that.
Very nice work, Alex. So I think the results of these dust contributions that you have listed out from the trial would make water managers very happy. So I'm just wondering, since you have limited sampling over 1 year, do you think how representative this is?
Yeah, so this is just a snapshot, and I think the other thing is you look at the location of our sites. Our detection of playa, we're not really, during the high playa seasons, we're not looking downwind of where the playa would be. So, but I guess this is I think this is a good indicator playas are emissive, I think. But it's a good indicator that transport is north as well. Because if they were transporting north and they were emitting, it'd be nice to do this for 10 years. But in 10 years, the Salton Sea is going to be, there's going to be twice or 3 times as much playa as well. So I think semi-representative, representative for the part of the basin we're in, but definitely not for the rest of this. And really it says that perhaps these areas north of the sea don't have to worry as much about playa emissions. But that doesn't mean we shouldn't worry about playa emissions because although these contributions were low up here, this San Bono site during these months, and this sample is 10 times what it showed. So it was really important here. And there are people that live right down there. There's not many of them, but they live there, and there's still people who want to live their lives. So, yeah, does that answer? Okay. Well, I was going to ask you.
So, what are they mainly growing in that area, and historically too?
So I know it's field crops is something they own. So like alfalfa and stuff. it's a wide variety. So they grow most, I think most of our winter vegetables actually come from places like this. But they grow things like strawberries, and there's orchards out there too. Musetto actually might have a better answer because he worked it. But it's a really wide variety. There's lots of agriculture.
Okay.
And so, I mean, I know the northern part of the basin is a lot of dates, but the southern part of the basin seems to be very varied.
Yeah, because I think in that area, there's been historically, maybe not now, but historically a lot of OC, organic.
Yeah.
And I'm wondering, if you guys have ever looked at or thought about looking at the presence of contaminants in the dust that's being mobilized.
So we've thought about it, and I talked about it a few times. And I think the soils we actually collected for that first project, one of Jay Jan's postdocs actually looked at them for a few different things. I think he kind of did something and then kind of put him in now in a cupboard somewhere. But that's a big worry. And so everything we looked at here is all inorganic. So we haven't looked at anything like pesticides. So
because those kind of crops are pretty insecticide and fungicide intensive.
Yeah.
When you go into sort of high commodity crops like that, I'm assuming there's probably been historically runoff or movement.
This is all essentially sustainable runoff. All the way that goes in this kind. So I think our work isn't really informed enough to say anything about that specifically, but that I know that's a large concern is that especially the deeper sediments that maybe have more accumulation of stuff, that these might become more and more toxic. So it seems like from a metal standpoint, what our PM10 stuff look like is that maybe it's just the mass that matters, but from from an organic standpoint, pesticide standpoint, it might start to matter more. So I think that if we have stuff there at some point, that'd be something that would be of interest.
Yeah. I was also curious, so why are there sites on the west side of the Salton Sea? Is that a logistical issue?
So simply, short answer is yes. We weren't, so I think this was in collaboration with Emma Harrison's lab, and they had kind of chosen the sites by the time we had come on.
Okay.
And so they were in charge of the field park originally and planning that field park. But yeah, I would love to have something on the side. And we also had some issues with sites we thought we were going to get to change last moment because we didn't get the permission we thought we were going to have. And so we would have had one on the west side. And that's actually a great question because there's an off-road vehicle park here.
Yeah.
That's really important. You can imagine it's very important for the overall test budget. So there's a good chance that some of that local illumination is probably controlled by that off-road vehicle park, and that we can't really just say that confidently. I think it's a big, of the limitations we have, that's a huge one, is that we don't get that west or even the south side, which would give us a better idea of the agricultural use. So.
I guess the last question I had was on the uncertainty part. So it looked like, based on those two graphs you showed with the refraction index, that you had more variability sort of in the beginning, and then the confidence intervals sort of came together,
And so that's actually kind of just experiment. That's just looking at the raw data. It's not using that tool.
I was wondering if you were thinking about uncertainty in the context of that sort of variability. So in other words, are there certain variables that you haven't necessarily that are driving?
Yeah, and so that's kind of
variability.
That's trying to what we're trying to constrain there with that tool a little bit is that when you have smaller size distributions, you're more close to your detection limit for those. So you're still saying, okay, I'm confident in this, but you're assuming your observations are right. But when you have smaller size distributions and smaller absorption measurements, those uncertainties are going to be much higher.
Okay.
And so yes, I think if we were to go to those, if you were to look at those K-value graphs and say, is that real, that kind of drop in absorption we see in that first 15 minutes? I'd say I couldn't confidently tell you yes. I'm much more confident when the size distribution is stable in those later measurements.
Okay.
That it's,
So it's like reaching like equilibrium.
you're getting enough that you can see it confidently. So we have some. We have some kind of checks on there.
It's on slide 26. I think you're right. Yeah, you got like 90. Slides.
Yeah, so I prefer slide animations, and sometimes
I think it's slide 26.
Yeah, and so this is just inter-experiment variability. So we ran these on triplicate. But you can see these are a little bit bigger. Our experiments themselves seem to be more. But you could potentially say that we have we do cut off, there's probably a measure there to be here that we say, okay, We know that's not true. But I'd say we're less certain in this than we are in this.
Really good and informative presentation, by the way. I was just thinking about it. Would planting like salt-tolerant crops like phaerophytes and not playa fields help alleviate the issue?
Yeah, I mean, so like vegetating these playas is one of the things. So I don't work specifically on like restoration and mitigation, but that is one of the strategies they use is to try. But as you can imagine, these are very salty. It's not just slightly salty. You have salt crusts that are forming, which is a good. So you have to have very salty tolerant jobs. One of the big issues is they're regenerative. So if you like get the salts out, you still have salts that are moving up through the soils. So I think they've had some success doing it, but I think if you had plants, you potentially even increase the evapotranspiration, you would get more salt moving to the top. So I don't know if it's a long-term solution.
Other questions?
I have one more.
Yeah.
So, how do you manage that then? I mean, do you irrigate the playa so it doesn't?
Yeah, so I mean, I think irrigating the playa is probably, I think, it's one it's better to think about ones like they've done more stuff there, but they'll do things like cover it with water or cover it with gravel because then it's much harsher. It's not really being trained. The kind of thing that they're using right now that I think the jury's out on a little bit is they're just plowing it. So they have like furrows because the theory is that wind needs a fetch to and then if you make the wind move up and down more, it can't get as fast sort of thing. So it makes the ground rougher. It's harder to get more lessons. That's the one that they're really trying to apply right now. I don't know if long-term wise, so it's really cheap because you can just plow it. But I think that's what's really attractive. But long-term wise, those things may just become again like this. I think one of the issues is these things are active. They're very dynamic. Like you can go out there today and it can be different. It will be very different than it will be in a month because of the water underneath it. So the water, like the evaporative transpiration and the salt crust formation is very dynamic. But yeah, water on top, gravel on top, vegetation. I don't think they're trying to pavement. There are
like a walking trail, right?
Well, a little bit of it would help. But you're talking about like the kind of like from the shore to the sea.
Yeah.
It's probably on the order of like a mile. Right?
Oh, okay.
So yeah. So I think that's just the skill thing is hard. And so no matter what you have, it has to have a per acre cost that's cheap. I think even the plowing, it's like a few $100s per acre. So when you have it's like 75, when you have 100,000 acres or something like that, it's quite expensive. So.
All right. Maybe we let Alex take a break and then I'll relate. Thank you.